Welcome audience. So we start with another lecture on, in fact, lecture number 4 on controlled thyristor rectifier as part of the course line commutated and PWM rectifiers. So as we can see, we are still in week 1, and this is the last part of week 1 where we are trying to actually cover the diode and thyristor based rectifiers, single phase and 3-phase. Diodes we have already covered, and now we are going to cover briefly thyristor based rectifiers. Now this is already covered in our India. In India it is covered as a first course in UG Power Electronics. And so I will briefly touch upon the important aspects of thyristor rectifier, and we will at the end see the problem with a thyristor rectifier in terms of the input power quality. And then we will go into some of the solutions in week 2 as part of multi-pulse rectifiers and THD and power quality issues. So controlled thyristor rectifiers, as we know, is that we use these kind of thyristor rectifiers to convert single or 3-phase fixed AC voltages or into a variable DC output voltage. Okay, when the power level is high, actually these thyristor rectifiers are very popular in earlier days, and they were used extensively in high-powered DC motor drives to control the output torque and speed. So as long as DC motor drives were popular, thyristor rectifiers were also very popular. But nowadays DC motors have kind of like been all replaced by induction motors or PMSM, and so thyristor rectifiers are no longer used. They are still used in high voltage DC transmission again, but it is this kind of rectifiers are getting slowly replaced by voltage source converters. So in those LCC based HVDC transmission, line commutated HVDC transmission, we are seeing a transition from LCC to VSC based HVDC transmission. But so that's why in this course these thyristor rectifiers have been kind of like they have been stressed in a very minimal way. Okay, we are trying to just cover, because of historical reasons, we are just trying to cover a little bit of thyristor rectifiers without going into too much of details. So if you see the thyristor rectifiers, we have both the single phase and the 3-phase variants are possible. So here you can see that this is the single phase variant and here is the 3-phase variant. Okay, and we have a control circuit, and this control circuit is used to fire the thyristors. Okay, and so we can actually get a output voltage here which is variable. Okay, so this voltage is variable, so we can control the output voltage. More specifically, we control average output voltage. Okay, we control the average DC output voltage. This is what is controllable from a thyristor rectifier. Okay, and how do we do it? We will see that here. So if you start with the most basic rectifier, thyristor control rectifier, we have an AC source here, we have a load here, and we have a SCR or silicon control rectifier, or commonly known as thyristor. Now for the SCR to conduct, we have this SCR must be forward biased, which means anode voltage must be more than the cathode voltage, and this gate current is positive. So this is the gate current here, which must be positive during the time when the SCR is being turned on. Once the SCR starts conducting, the gate current actually can be removed. Okay, and the SCR will remain turned on until the current IS, in this case the anode to cathode current, as long as it is positive, the the SCR will be turned on. So in this way we can say that the SCR is a semi-controlled device, which means you can turn it on but you cannot turn it off. The turning off of the SCR is dependent upon the external circuit. Okay, now so if you see the waveform, you can suppose here when you fire the SCR, we use a word firing angle, okay, which we denote by the letter alpha, firing angle or delay angle. Okay, and here it is, this is this alpha here. Okay, this is where the pulse, okay, the gate pulse to the SCR is given. So here is your supply voltage. Okay, this is the supply voltage waveform, and when the SCR turns on, what happens is, if I assume that the SCR is a perfect device having no drop during the on state, then the output voltage V0 will exactly follow the input voltage. Okay, so this is kind of like a short, and so the output voltage will be exactly equal like a input voltage. Of course, because this is a resistive load here, the current which is flowing here, so this is the output current, it is a resistive load, so it will follow, or it will become an exact replica of the V0 voltage, right? So this is where we have shown this one with a magnitude which is equal to Vs by R. Okay, now the current will be equal to 0 at this point of time. Okay, and so as we have said that the SCR remains turned on until the current IS is 0. So therefore at this point here the SCR turns off. Okay, the current has become 0 and there is no more gate pulse, and so SCR has turned off, right? And so the output voltage, if we see here, is looking something like this. Okay, this goes like this and it is not turned on, so the SCR is not turned on. Okay, and then again up to this point, and in the positive half again we give the pulse, next pulse. This is the next pulse. Okay, so during this point here, even if we give the pulses, the SCR will not turn on because now the polarity of the voltage is opposite. Okay, so SCR will not be forward biased. So therefore the output voltage, of course we understand the output voltage will be somewhere here, the average output voltage. So this is the average output voltage, and the average output voltage can be mathematically determined by using this expression here. Okay, so the average output voltage V out is 1 by 2 pi. So this is the total time period, this is the total time period which is given by T, and we can also write it as 1 by 2 pi. Okay, so 1 by 2 pi and integrating from alpha to pi. Okay, so this is the alpha angle here, and corresponding to alpha, so alpha to pi, so this is the alpha to pi. So here this is T, so if I take it as omega T, then this is alpha to pi, otherwise we have to use this expressions. Okay, so we can actually change the variable, so that is what, so let me make it properly. So if we use theta here, theta equal to we use this change of variable, we make it theta equal to omega T. Okay, then this angle will become alpha and this angle will become pi. Okay, instead of using T. So that's what we have used here, 1 by 2 pi. Okay, alpha to pi and Vs sine omega T, d of omega T, or you can also say Vs sine theta. So this can be also theta and d of theta. Okay, and this value will come out to be Vs by 2 pi 1 plus cos alpha. and we understand that this output voltage V out can be changed by changing the firing angle alpha, right? So if we use an alpha which is equal to 0 degree, we get the same performance like a diode rectifier. Okay, and when we have alpha equal to pi, okay, so here the 0 less than alpha less than pi, if we get alpha equal to pi, then obviously we understand that so if the alpha is increasing up to pi, then we do not get any voltage output, right? So the average output voltage will be 0. So now let us see what happens if we instead of an R load, we use an RL load. Okay, and as I told you, SCR or thyristor rectifiers were most frequently used for DC motor drives, and in DC motors the winding of the motor is considered to be an RL load for the converter. Okay, so that's why it is important for us to analyze the RL load operation of the SCR of the thyristor rectifier. So in this case, what happens is that at t equal to t1, just like before, so at t equal to t1, like this point here, the SCR is already forward biased because the anode cathode voltage is forward biased, and we give the firing angle. Okay, so here it is turned on by giving a gate current pulse, right? So at this condition, what is the governing equation? So once the thyristor has been turned on, we assume that this is shorted here, and so Vs minus Ris minus L di dt equal to 0. Okay, so that is the governing equation, or rather I can say in another way, L di dt is Vs minus Ris and is equal to is greater than 0, okay, during this point, because of the fact that all this Vs is more than Ris at this point of time. And after t equal to t1, we find that the voltage Vs is also increasing in magnitude. Okay, so because it's a sinusoidal voltage source, so the instantaneous magnitude of the voltage Vs is increasing, and so this L di dt value will go on increasing, and we will find that the current is also increasing. Okay, the yeah, so this is the current, so this is the waveform of the current, and the current will go on increasing. Okay, and since the SCR is fully turned on, so this is the output voltage, so this output voltage comes here, and so the output voltage exactly follows the input voltage. Okay, the current goes on increasing. Okay, Is increases here, but it will not go on indefinitely, right? Because at some point, okay, at some point in the AC waveform, because now after some point the source voltage starts to drop. Okay, and this condition will not hold true. Okay, and what will happen is after some point L di dt will equal to Vs minus Ris will become less than 0. Okay, and the current will then no longer rise, and then the current will start to fall here. The current will start to fall. Okay, so this is the condition here where Vs minus Ris is less than 0, right? So initially the current rises, and then the current starts to fall. It will go on falling until, as I told you, that you cannot turn off the thyristor, and so the current will fall, and at some point eventually at this point of beta, okay, the current will become equal to 0. As long as the current is positive, the thyristor will go on conducting, and in such a way that even if, so here is the trick, even if the source voltage, okay, the source voltage here has gone negative. Okay, after this point the source voltage has become negative, and the output voltage which follows the source voltage has also gone negative, okay, during this point. But since at this point the current is still positive, so the SCR will go on conducting up to the point beta. Okay, at beta, what happens? So what happens during this time is that there is a stored energy in the inductor. Okay, you have stored some energy in the inductor in the form of this half Li square. Okay, there is stored energy in the inductor. That stored energy will force the current to continue. Okay, and it will force the SCR to conduct in spite of the fact that the source voltage has gone negative. Okay, the source voltage has gone negative here, but the stored energy in the inductor will force the SCR to go on conducting till the point beta is reached, where the stored energy in the inductor becomes equal to 0. Okay, so at omega t equal to beta, therefore the current goes to 0 and the SCR will stop now conducting. Okay, and again it will start conducting in the next cycle when you again fire it with an firing angle alpha, right? So we can now find out what is the average voltage. So we can find out the average output voltage by averaging this waveform, right? And now we will average the total time period is of course 2 pi like before, and we will average the from alpha to beta. Okay, we start at alpha and we end at beta, and the output voltage waveform has this expression, okay, Vs sine theta d theta, right? And when you substitute these values you will get this one. Okay, so you can see here that depending on the average output voltage depends on both the angles alpha and beta. Alpha is called the firing angle and beta is called the extinction angle. Okay, so both, it depends on both of them, and we can see how much is the average output voltage. Now one thing that we would like to see is that what happens when the resistive part gets smaller and smaller. Okay, what happens here is that when the resistive part becomes smaller and smaller, then this angle, this beta angle starts to expand. Okay, so it is as if like, so for if the resistive part is smaller and smaller, then somewhere the beta will extend. Okay, so alpha, it is starting here and it will end here. Okay, and subsequently also it may happen that alpha is here and beta is here, okay, before the next alpha starts again, right? And so what happens at some point, okay, the current will start before it reaches 0. Okay, for some angle, so like this, you can see the blue waveform here, the current is no longer coming to 0 and it again start like this. Okay, so this type of current is called continuous conduction mode, CCM mode of the thyristor rectifier. Okay, you have seen this also in DC-DC converters. So this is the CCM, so continuous conduction mode of thyristor of the current. Okay, and so the other operation where this starts from alpha and ends at beta, this is called DCM mode of operation, discontinuous conduction mode of operation, which means the current will start from 0 and before the next firing angle it will come back to 0. But in CCM it will never come to 0. If the value of L is very, very large, then we get something like this. With negligible ripple, a very flat kind of waveform. Okay, and this happens typically in a motor drive. Okay, we will see this one sometime later, how this happens when we take up the example of full bridge rectifier. Okay, one small thing here is that, suppose in this case what happened, you can see here that you had a output voltage which has both positive and negative parts. Okay, which is not good, because you want to produce an output voltage which is always positive. Okay, so in many cases you want to have the output voltage only positive. You do not want negative half of the AC cycle coming into the output side. So what can you do is that you can put a freewheeling diode. Okay, so if you put a freewheeling diode, what happens is, as soon as the voltage at the output starts to conduct, as soon as the output voltage starts to go negative, this diode will start to conduct. Okay, and so the output voltage, okay, the V0 output voltage will go to here. It will not go to negative anymore. It will be 0. Okay, and then again it will start like this. So this is the waveform. Okay, of course you can control the output voltage by changing the firing angle alpha. Okay, and yeah, so we can use this circuit if we see that we do not want any negative voltage on the output. Okay, fine. Now let us see the full bridge control rectifier. Okay, this is more common. Full bridge control rectifier is more common rather than the half bridge. Half bridge is good for understanding, but it has limited practical application. Okay, now in this case of full bridge, what happens is, two paired, like exactly like a diode bridge rectifier, we have studied it. Okay, so a pair of thyristors will be conducting. So for example, this and this will conduct, and this will conduct. Okay, so suppose you give a pulse like 1 and 2 here, and 3 and 4 pulse on the negative half of the AC cycle. Okay, so now we will get this voltage output here. Okay, and so we the current will also, so because this is a resistive load, the current is shown by this dotted line. And similarly, in the negative half of the AC cycle, we also fired the thyristors and we get one portion. So we had this problem. So now we are getting more voltage, right? We could not use, in a half bridge control rectifier, we could not use the negative half of the AC cycle, which we can now use by using a full bridge control rectifier. And you can see here, we have taken this from Wikipedia, an animation, and you can see here how the output voltage is varying as you shift the value of the alpha. Okay, so how much is the average output voltage? Average output voltage, again you can integrate. So now we will integrate. This is the value pi, this is alpha. Of course we have to use omega t here. So 1 by pi alpha to pi, okay, Vs sine theta d theta, right? And so we get this value of Vs by pi 1 plus cos alpha, right? So again, this alpha, by changing the value of alpha, you can vary the average output voltage. Now here also we can have both continuous and discontinuous conduction of the thyristors depending on the value of the L here, and these are shown here, and I will not cover this in details, and I expect that you have already covered as part of your first course in power electronics. what is important to note here is that here the current comes to 0. So this is the DCM mode of operation and this is the CCM mode of operation. And here in DCM mode, the current comes back to 0, again goes to a peak and comes back to 0 like this. Whereas in CCM, the current will never touch 0. Okay. So this is how the thyristors will will conduct in this. Okay. Now, when you have a large motor load, of course, then this RL load we replace it with a constant current load, right? The reason being that the time constant of this RL load is so high as compared to the 50 Hz AC sinusoidal impressed voltage or the source voltage. This has a time period. The AC waveform has a it alternates every 20 milliseconds. Okay, the time period is only 20 milliseconds. But this RL load of the motor, the time constant can be several hundreds of milliseconds. Okay, so in that case, the load current does not change appreciably over one fundamental AC cycle. Okay, and so therefore we can replace the RL load with a constant current load. Okay, if you have a constant current load, right, then the waveform of the current becomes like a square wave. Okay, fine. And so when this is the source current waveform, this IS, okay, because this current is constant of magnitude I0. Okay, this is the magnitude I0 and minus I0, and so the diagonal thyristors are conducting, and therefore in one cycle this two thyristors 1 and 2 are conducting. Suppose here 1 and 2 are conducting and here 3 and 4 are conducting, and so the output voltage is something like this. Okay, output voltage is something like this, and you can see here that since the current is positive here, the voltage has gone negative. Okay, the voltage goes negative because the current is still flowing through the thyristors. Okay, so what is the average output voltage? Again, the average output voltage you can integrate 1 by, so this angle is alpha here, and it will go on till pi plus alpha. So integrating from alpha to pi plus alpha, and the time period is 1 by pi here. Okay, the time period is pi, so this is the time period, t equal to pi. So alpha to pi plus alpha, Vs sine theta d theta. Okay, and this will come out to be 2Vs by pi cos alpha. Okay, so the output here, since the alpha is between 0 and pi, we can say that the average output voltage can be positive or negative. Okay, you can make the average output voltage less than 0 even, so it can, the average output voltage can become less than 0. Okay, it is possible. Of course you will have greater than 0 possible. Now what does that mean? So basically it means, so this is where the average output voltage comes here. Okay, so a negative average voltage and a positive current. Note that the current through this is always this way. Okay, always in this direction. It is going from the plus to the minus. The current cannot change its direction because this is, you can see from the symbol itself, it's a symbol of a valve. Okay, it's a symbol, it's a diode thing. So it can carry current only from anode to cathode. It cannot carry current from cathode to anode. So therefore, the current will only flow from the plus to the minus terminal. Okay, but the voltage, that voltage V0, that voltage can become positive or negative. So what does this mean? A negative average voltage and a positive current. What is being said? So the power, okay, the power drawn by the load is now becoming negative. It means that this power is being fed back to the AC supply. Okay, power drawn being negative means that power is given back from the load into the AC supply. Okay, now this can happen, of course this will happen, this happens in many applications. Okay, and in particular when a motor is regenerating. Okay, since these thyristor rectifiers are used for DC motors, so when the DC motor is regenerating, basically it is sending back its energy into the supply. So the motor is actually braking, or the speed is falling down, and the kinetic energy of the motor stored in the rotational part, that kinetic energy is being transferred back to the AC supply. And this can be done by the rectifier by changing the firing angle. So we make the average voltage to be negative, whereas the current was still positive, and so the power will be then fed back into the AC supply. Okay, this is typically used for regeneration operation. This is not only true for DC motor, this is also true for AC motors also. All types of AC motors, induction motors, PMSM, they can also do the same thing. Okay, but we have to use a voltage source converter. We generally use a voltage source converter in that. Okay, so with this one we conclude our session, and I would like to see you once again in another session on the course Line Commutated and PWM Rectifiers.